change. All right, so to begin with here, we're going to look at the calculus relationship that exists, and it's real simple on this. Since derivatives are giving rates of change, if you have a position function, we talked about that last time. S is just the position, like the example we did on the first page. Then the velocity is the rate with it's changing. So the velocity, we either say ds over dt in the Leibniz notation, or we just say f prime. So that's the first derivative, is what the velocity is. Okay. Now the speed is an absolute value of the velocity. So you learn this a lot in physics. A velocity can be positive or it can be negative because it has a direction to it, all right? And then a speed must be positive. Okay, you're familiar with that. If you drive in your car, your speedometer doesn't have any negative numbers on it, right? It's a positive quantity, so it's an absolute value of the velocity. That's the idea. Okay, then the acceleration is the rate at which your velocity is changing. You know that from your travel in a car. You speed up, you're accelerating. You slow down, you're decelerating. That's a rate of change of your velocity, so that is the second derivative. Okay, so we usually notate like this. That's the second derivative of the position, or we do f double prime of t like that. Okay, so derivatives are a real big deal in physics. Okay, so if you go in a physics professor's office, his chalkboard will be full of derivative formulas and stuff like that. It'll be calculus all over his board. Okay, so here's kind of an example like this. This might be a position function right here. And what this would kind of mean is that would be like the beginning of your journey. T is equal to 0. You're at the beginning. You're at the point 0, 0. Okay. What's happening on this one is you're moving away from that, and then you're going back towards this. So if you look at this position, what you're doing is you're going in a negative direction, and then you change directions and go back to the beginning where you're back at a y value of 0, basically. Now what a velocity is a first derivative. So what is the value of the derivative right there? 0. So that would mean that you have 0 velocity. Okay, that's what that would mean, okay? And the reason it is because you're getting ready to change directions, okay? Now, what kind of derivative would you have here? What kind of tangent line do you have here, negative or positive? Negative. Okay, so you have negative tangent lines right there. Notice in this graph of a derivative, these are all negative values right there, right? Those are all negative values. Now, what kind of tangent line do you have here? You have a positive slope, right? So that means that the value of the derivative of that, or the velocity, is positive. Does that make sense to everybody? Okay, we've done a lot of talking about the graphs of derivatives. So the way I look at this is basically on this, when you're doing the velocity, it's negative, then it goes to 0 because you're changing directions, then it's positive, like that. Now the acceleration goes like this, okay? What kind of slope do you have on, if it's a line, isn't that a constant slope? So that would have a constant slope, okay? So that what that means is the acceleration would be constant, okay? So what I'm doing on this one is, and I gave you the function on here. This is t squared minus 5t. The first derivative is 2t minus 5, and then the second derivative is just 2. So that means acceleration's constant. That's why I've got the graph of the line y equals 2. Okay, does that make some sense? Okay, because you want to make the connection graphically between position, velocity, and acceleration. That helps you understand the content and the topics that you talk about in physics. Okay, so let's go to the next thing here. And what we're going to do on this is kind of a typical physics problem for, a Calc 1 student, is I'm giving you a position function. You learn in physics an actual formula for projectile motion. You don't have to know that in this class, but typically that's like your initial height right there. And generally what you have on this is the initial velocity. Okay, in this class, that's all kind of given to you, but when you study physics, you have a general projectile motion equation, which is a quadratic equation like this is. Okay, all projectiles follow a parabolic path, so we have that. And then generally, this has something to do with gravity right there. And what this one is they're saying this problem, you're throwing something on Mars, so every planet has a little bit different gravity to it. And like on Earth, do you know what the gravity is from your background? Okay, 32 feet per second or 9.8 meters per second. Okay, those are kind of the big deal there. The moon has a different one, Mars has a different one, and so forth. So what we're going to do on this is we're going to do some pretty simple calculus. We're going to determine the velocity after t seconds. So when we do the velocity, you want to write down v of t is just s prime of t. So you just take the first derivative. And that's a real easy one. That should be negative 12t plus 64. So that's the graph of your velocity. Now, I think on your handout, did I put a graph? That may have been something I added. It doesn't matter. You can just refer to this graph. So I just took my graphing calculator and graphed out the position function. So one thing that this is saying is your initial height is 192. And as the projectile is hurled, its height changes. It eventually reaches a maximum height, then it eventually goes to the ground like that. So that's how a projectile would look. Okay, next thing I want to kind of look at here is this thing. So this says the highest point is reached at an instant when the stone changes from moving upward to moving downward. Okay, so this would be like when you're moving upward, the velocity is positive. And then when you're moving downward, the velocity is negative, okay, like that. So it must occur when the velocity is equal to 0, okay? And if you look at my graph, that should make sense to you. You have a positive sloping tangent line here, right? Right there, that velocity would be positive. Right there, the velocity would be 0, and then the velocity would start going negative. Okay, does that make sense? All it does is just means the direction. You're going up, velocity's positive. You're going back down towards Earth, velocity's negative. Okay, like that. Okay? All right, now what we want to look at next here is it says, what is the height of the stone at the highest point then? Okay, so one way you can figure this out is if you want to find the height of the stone at the highest point, what you can do is you just set the velocity equal to 0. Because we know when the velocity is 0, we're at the high point, right? Because it's going to change directions, okay? So what we do is we take the velocity that we found in part A, which is negative 12t plus 64, then we set that equal to 0 when we do that, and then we'll have the time there. Now we have to just find the time. We ultimately have to find the height too, though. Okay, does that make sense why I'm doing that to everybody? Okay, velocity is 0 at its maximum height, right? Okay, is that sensible? Okay, tangent line's horizontal, okay? All right, so let's solve that equation. So, now I don't know why I put a plus 0 there, though. That should be an equal 0. So, I'm going to go ahead and just move that to this side. Then we can take our calculator and just get a decimal on this, I think. So we can go ahead and do that and see what we get there. So, let's see. Did I bring my calculator? I think that's 5 point something. 5.3. It's got repeating decimals on it, so let's just round that off to t is approximately 5.3 seconds. Now, if you look at the graph that I did on my graphing calculator, this 1, 2, 3, 4, 5, 5.3 right there, that pretty well corresponds with what we would expect. So visually, that looks like that's correct. Okay, so what we have to do, though, is we have to find the height. Well, we know that the time that happens, so if we find the height, you got to go back to that position function. So what you got to work out next is you got to work out s of 5.3. So you want to go back to this function I got highlighted in yellow here and just plug in 5.3. So we're going to have negative 6 times 5.3 to the second plus 64 times 5.3 plus 192 like that. Okay, then I'll take my calculator out on that, and then we can put that together also. So I think I've already worked this out. And with this one, I've got I get about 362.7 feet. I do want to get my calculator out and kind of check over these things too, because I want to show you a couple of things on your calculator as well. But that right there, you just need to use your calculator on to get that put together then, okay? All right, let me pull up this calculator for a second here. And let me show you a couple things. I would like you to do this on your calculator because it really is a nice thing to be able to do, you know, for checking and verifying when you're doing these problems, okay? And I'll show you a couple things you might not know too on a calculator. Okay, so what I'm going to have you do is we're going to go ahead and put in the position function. That's what I'm interested in you graphing. So I'm going to put in -6, then I'll put in x to the second plus 64x, and then plus 192. And I think I got a 54 in there, so let me fix that. Okay, so there we go. Okay, and then for a window, I'll tell you a window to do. We're going to do something pretty logical like this. And since I got a maximum height of 362, that tells me how I want to do my y-axis. So you want to get that in. Y-axis, this is t. Let's start t at 0. Let's take t out maybe to 11 or 12 or something like that. We know that it reached its maximum height at 5.3 seconds. That's how I'm kind of reasoning that out. Now for the y minimum, we're going to go start at 0. That's the ground. Then we're going to go up maybe to 400 because we just calculated with some calculus and basic math that that height was 400. Then we're going to scale that by 100 like that. Okay? So you want to get that window put in. I'll slide that over there so you can see that. Then you want to go ahead and graph it, and you can see if you get the same graph that I have here. Okay? Okay, I probably should. Let's take the x max out maybe to like 15 or something like that. Okay, maybe 16, something like that, because I want to get to the point where it reaches the ground, because I think that's another part of the problem that we're going to find out is find that point right there. Okay, everybody with me on that? Okay. Now, what we can do on this, so you can check this real easily. So this trace, so if you go trace, if you want to try this, put trace and then put 5.3. Actually, I'm going to put a bunch of decimals because it had repeating decimals we rounded. And then what happens is, see, if you can see that, can you guys see that that's 362? I think that's what that's saying. I think that's what we got when we calculated that out in the last problem, right? So you can check that visually when you do that then, see, okay? All right, so that's the idea. And the other thing is, like if you traced at 0, all that's doing is that's giving the initial height of 192 like that, okay? Now, if you don't know how to do this, I like to show this just because I think it's cool. Whether you will, I don't know. So on a TI calculator, most of them, if you go y equals, you can get your cursor going there like this, and it's a little bit different on this calculator. If I get the cursor right there and press enter, then you can go down and let's see if I remember how to do this on this calculator. Yeah, you can kind of change these things to different things. There's the one that's a ball, okay? So we did that ball. So if you change that to a ball like this, okay, this is what happens, okay? Let me see if I can get that graph now. Oh, crap. The way they did this on here always messes me up. May not be worth showing you. Let me try one more time, okay? So you're supposed to change that thing to ball. Then I'm supposed to do okay, if that'll let me do that. I don't know. Oh, I know what I got to do. I got to go like that. Okay. Okay. After all that work, this better be really cool because it took me forever to do that. Ooh. So you can actually make it kind of model a projectile. I think some of you were in my trig class. What I did last semester with trig is we did a pendulum, a project that made the pendulum swing, and that was kind of cool. So we did that. So I always think that's kind of a cool thing. All right, so let's move on and let's do the next thing. So what we want to do is, when does the stone strike the ground? Well, the thing on this is, when it strikes the ground, the thing that's happening on this when it strikes the ground, okay, we don't know what the time is, that's what we're trying to find, but we do know the height is 0. We know that. Okay, so what that really means is, remember, S represents the height. So what we want to do on this problem is we want to go ahead and let's write down the general formula on this like this. So that is S equals negative 6t to the second plus 64t plus 192. So we want to do that. So if we want to find when it reaches the ground, what's the deal with S? What did I say? That's equal to 0. Okay? So what you're going to have is you're going to have a quadratic equation that you can solve, and there's different methods. This thing may be a quadratic formula thing. That's what you get into most of the time. So I want to do that, and then I want to show you how your technology could figure that out for you anyway. So one thing I notice on this one is I think this thing may divide by 6 or negative 6. I think all these numbers divide by negative 6. So I'm going to do this. I'm going to have you do this. When you go to the quadratic formula, it's a lot easier if you do it this way then. Okay? What's that?
64 doesn't divide by 6.
No, it doesn't. You're right. It divides by 4, but 6 doesn't. Let's see. Everything divides by 2. That may be as far as we can go on that one. I think it is because of the 3. Yeah. So let's divide by negative 2. And I could have actually done that and got a decimal, but I want to try to do it better like this. So that's 0 equals 3t to the second minus 32t, and then that is, what's that, 108 or 80, 90, 96, is that right? Yeah, that's right. So that's 96 like that. Okay, now I don't think that factors. Okay, so I'm just going to go directly into the quadratic formula. So let's go ahead and pull out the quadratic formula, which is negative b plus or minus square root of b squared minus 4ac over 2a. Okay, so we want to do that. And then when we solve that, that'll give you the time when you're on the ground like that then. And we'll just use a calculator on this. So we're going to have negative 32. And let's see, we'll have b squared, negative 32 squared. And we'll have 4ac. C is negative 96. And all over 2a like that. So a is 3. So I've got that. So I think I got everything plugged in. I'm just getting my calculator out, and you can do that with me, and let's see what we get here. So what I'm going to do is I'm just going to do the discriminant, the part under the radical, just in one step on my calculator, and put that all together. Okay, so I think on this I'm getting like 2,176 over 6. And then when I go through and if I do this, what I'm going to have is I do two things. I do 32 plus that radical, and I'm just going to use my calculator on that radical. And then I can do 32 minus that radical over 6 like that. So let me pull up my calculator and just do that real quick. Okay. All right. One of those answers is going to give you something that's kind of ridiculous. One of them is going to give you an answer that's solid. So if I do the 32, and so I'm just going to do this one step, plus the square root of 2176. I'm going to get that answer. Then I'm going to divide that by 6. Let's see if I get a fairly logical answer. That seems pretty logical. So that would be t is about 13.1 seconds like that. Okay? This one over here would give you a nonsense answer, because if you did 32 minus the square root of 2176, you get a negative number there. Okay, so say I'm getting negative, so that one's nonsense. Okay, all that one would do is that actually just gives the x-intercept of the parabola. It doesn't give the one that's logical in the context of the problem. Okay, all right, everybody okay with what I did there then? Okay. Now, one thing you can do on this too, if you don't know this, not all students seem to know this, is I'm going to go back and get my graph on here one more time, and I want to show you one other thing that you can learn to do, that kind of comes in handy with your calculator. Let me get back to getting a solid line on here. Okay, and let me graph this real quick, and let me show this to you. So you can actually, your graphing calculators generally will find zeros for you. So if you want to try this, you can do this. If you have your graph up like that, this is called a zero, like you would have learned in college algebra. So you can go second, trace, to open up the Calc menu, and then you can go to option 2. Okay, now option 2 is going to find a zero for you. What it's going to do, it's going to ask for a left bound. That means you need to get the cursor a little bit to the left of where that intercept is, like that. So I just kind of close in, and it doesn't have to be, just relatively close is all it has to be. That may even be good enough right there. Okay, so I just kind of do that, press enter. Now it's going to ask for a right bound, so I got to get that cursor a little bit to the right. Now I'm going to get out of range here, so I may have needed to expand that, but it may still work. So I do that, then I press enter, and then generally it calculates it for you. So that's 13.1, that's what we got anyway. So that kind of comes in handy. It keeps you from having to do the quadratic formula, right? Okay, so you can do zeros. If you need to make a note of that, it's second trace, option number 2. Okay, and then just get a left bound, a right bound, and it'll calculate it out for you. Okay, is that good? Okay, you guys ever seen that before? Some have, some haven't. Okay, that's a nice thing to know for this class and for higher math. Okay, so let's see. Now the next thing is, to finish this problem up, is it says, so we now got the stone strikes the ground. One thing I wanted you to put on this, the stone strikes the ground when S of t is equal to 0, like that. Okay, so that's the kind of the key thing on that. And that just ended up being for t is equal to 13.1 seconds. Okay, now it says what velocity does the stone strike the ground with? Well, what we need to do on this, we need to go back to where we computed the velocity. So let's write down that v of t is negative 12t plus 64. Okay, so what we're going to do now is we're going to find what is the velocity when it struck the ground. Well, when did it strike the ground? What did we find? 13.1 seconds, right? Okay, so what we're really going to do is we're going to do v of 13.1. So we're just going to calculate that out. So negative 12 times 13.1 plus 64. Okay, that will give probably about, I think, negative 93 or something like that is what I had here. So let me make sure I got that. So I got 13.1 plus 64. So yeah, that's negative 93.3. And I think this thing, the units in this problem, I think were, if you go back to the beginning, it was, you had feet and you had seconds. So that would actually be feet per second, like that. Okay, and that would be the answer. Okay, that's a classic Calc 1 problem to show students with physics. Okay, very classic problem. That's always tested over because it's a good application. Okay, now let me ask you this question. How come the velocity turned out to be negative? Right, it's going in the negative direction, right? It's going towards the ground. That's why. Okay, so the math that doesn't lie. It all works out beautifully for you. Okay, all right. Is there any questions about that? Okay, all right. Hopefully that kind of helps you get a beginning understanding of some of the things we use derivatives for. There's tons of applications to this. Okay, so that's just one of them. Okay, so I'm going to have you go to the next page, and what I wanted to look at on this mostly just has some terminology in it that I wanted to look at a little bit. So, for instance, this is what you'll learn in physics. So, this is what we call the projectile motion equation, and that's actually what we just did. S naught is the initial height. Okay, you can write and know that if you want to, although you don't have to know this in this class. You'll learn this in physics. That's the initial velocity. Okay, and then g is like the gravitational constant. Okay, like on the Earth, 9.8 meters per second. Squared is the acceleration due to gravity, or 32 feet per second squared is in those units. On the moon, I think that gravitational constant is something else. I think it's 1.62, like that. So what this is saying is we're doing the derivative. So the velocity, when you do the first derivative, this thing right here would be the velocity. Okay, so I just did the derivative of that. Power rule, that would be gt. Derivative of v naught t is v naught. Derivative of that constant 0. So that would be the first derivative. Now, what's the derivative of gt plus v naught? Well, what's the derivative of something times t? The number in front, right? And then the derivative of that velocity would go to 0. So the second derivative is just the gravitational constant. That's what that is. Does that make any sense? Okay, now that's a formula that's the general projectile motion equation. So what I was going to show you on this is the Earth's gravitational force is, this is in meters per second squared, and it's negative. Okay, and then this is the gravitation at the moon. So if you go through and do that, you get 6. So that just means the Earth's gravitation is about 6 times stronger than the moon's. Okay, so that would be the idea. All right, so we know those things, and all that stuff when we went to the moon was experimented on and verified. Okay, so that's kind of a cool thing. All right, so let's see. A couple other things that we want to look at here is just a couple of things from the book that I wanted to go over. What this statement is saying, if this is large, now see what that is that's a rate of change. So if that is large, that means a very large derivative. That would mean that it has a very steep tangent line slope. Then it's going to say small changes in x will result in really big changes in the value of y. Okay? What that's really saying is something like this. If you had, say for instance, you had x equals 1, you had a curve that did something kind of like this, okay? So what would happen on this is, since the slope is real big, if you made a real tiny change in x, that makes the y values pretty big too. The steeper that is, the bigger that change in y becomes. Does that make any sense? Okay, that's just because we have a big rate of change. That means a steep tangent line. Okay, so let's make sure we know this. What's the difference between velocity and speed? What did I say speed was in relation to velocity? Absolute value, right. Speed's always positive. So the speed of an object is the absolute value of its velocity. You want to be sure you know that. So like on the problem we did before, when we had the velocity being negative 93, the speed would be positive 93. Okay, so that's the idea. And then the velocity encompasses the direction, like we talked about, that the object is moving, while the speed does not. Okay, that's the idea there. Okay, I want to look at this problem number 6, kind of a thought problem. And I'm going to give you an example that will help you understand what this is saying. This is saying an object moving along a line, and that's real key, has a constant negative acceleration, and we're going to describe the velocity. So let me give you an example of that. So let's say, for instance, that we have something like this. Let's say that we have the velocity. Let's say that we have something like negative 3t plus 5 or something like that. Okay? Now, the acceleration on this, what did I say the acceleration was? It's a second derivative, right? So the velocity is the first derivative, right? So the acceleration would be the derivative of the velocity, which is what? Negative 3. And it's constant. That's why I made up the example I did, because that's what the problem said, is it said it had constant negative acceleration. It's never going to change. That would be an example. If your velocity is represented by a linear function, then your acceleration is constant. Well, let's draw like a real simple picture of this velocity here. So we know if we graphed this velocity, you would have a y-intercept at 5. Then you'd be sloping down 3 over 1. I'm not going to do that super accurate because it doesn't matter anyway. So that would be the graph of the velocity. Okay? So what's happening on this is basically this. If you went through, and it kind of goes like this, you'll kind of catch on to this as you do this. The velocity is a line. that's sloping in some way. So therefore, the position is a quadratic. So what you would kind of have on this, if you reason this out on here, what you would end up having with here is your quadratic would do something kind of like this. The velocity would be equal to 0 in here somewhere. So what's going to happen is, if the object is moving in the positive direction, okay, then the velocity is going to be negative. So what you would have on this is, and I'm not going to explain to you how I'm getting this, but S of t would actually be negative 3t to the second over 2 plus 5t. End of the semester, we learned how to do integration. Okay, so what I'm saying, don't worry about how I got that. I can't explain that yet. But if you graphed this thing, this position function, it would end up being a parabola that kind of looks something like that. So the idea is, if the object is moving in the positive direction, okay, then what's going to happen is you're going to end up having some sort of the velocity is going to end up decreasing. And then if you're going in the negative direction, then the velocity is going to end up increasing like this. Now what that means by that is basically this. So if t was positive, what's happening on this is this velocity, and like, let me stand up and kind of show you what I mean by this, is what's happening on this is, the velocity is the slope of that tangent line, right? So that thing isn't that decreasing in slope? Yeah, I mean, that's a real big positive number. That's 0, now it starts getting to negative. So if you're moving to the right, like that, then everything's going to decrease, okay? If you're moving to the left, it just means backwards. And if you do that, if you're going this direction, what's happening? You have a negative slope, less negative, 0, and now positive. You see what I mean? So that's that. So what's happening with this thing, and the velocity shows that, is I made that example up because I had to come up with something that had a negative acceleration. Does that make any sense? Okay. Don't worry about where I got that. We learned that at the end of the semester. Okay. That's called integration. You can take a derivative and integrate it to get the function that was differentiated to get that. Okay. You'll learn that. Okay, so let's see. Let's look at, move on to this now. Let's go through this problem. Okay, which is pretty similar. Want to work with this just a little bit more. Okay, so this problem says you have an object is moving horizontally after t seconds. So we have that function. So we're going to graph the position function, which I gave you down here. And we're going to find and graph the velocity, and then we're going to answer several questions about that then. Okay, well, let's get our graphing calculator out and just do a graph of this quadratic. Now, you could do this one. I think this one factors okay, so I think I'm going to go over that also with you, but I'm going to go ahead and just have you put it in the calculator for now. So we have negative x to the second, and plus 4x, and minus 3. Like that, and then we're graphing from 0 to 5. They're giving us that window. So let's maybe go out a little further than that. Let's go to like 0 to, yeah, well, no, let's just stop at 5. 0 to 5, okay, like that. And then let's do y, oh, let's see, what did I have on that? I can just experiment with that window a little bit. Let's go up to maybe 6 or something like that. Let's go 0 to 6. And scale that by 1. I do want to go through how you could graph this one by hand too, because I want you to know how to handle that okay. So that would be my viewing window. And then graph, I'll just have you kind of sketch a little graph on that then. Okay? And actually, let me do this because I want you to see this a little better. Let's do, let's make the Y window go like -6 to 6. I want to see the area below like that. So I'm going to have you change that window like that. And then this will be a little bit better graph, I think, for what I want to show you. Okay, and so what I'm going to do here is just make a real quick sketch of this, okay, just on your notes, just for reference. And the key things on here is this is going to 6, that's -6, and that's 6 like that. Okay, and it looks like you have x-intercepts at 1 and 3, and I'll show you where that comes from too. Okay, so first of all, with this thing on this graph, one thing you could do with this one also is you can factor this one. So if you went through and factored a negative out, this is worth doing. If you factor a negative out, you would have t squared minus 4t plus 3, so I'm just changing the signs, and you would find that this thing is a trinomial that factors. So you'd have a negative, and if you factor that, you would have t and t, 3 and 1 to get the 3 with 2 minuses. Okay, now does that help you to make sense that that x-intercepts 3 and that one's 1? Okay, so see, sometimes these problems, if they're factorable, then you can do nice graphs on them pretty easily just by finding the intercepts like that. Okay, now the other thing is this y-intercept. That y-intercept is -3. Look at the function. Where is the -3 in the function? It's at the end. Remember, if you have a projectile, that last number is the initial height. That's what that means. Okay, now that, since it's negative, that would be in the negative direction, is what that would essentially mean. Okay, so now what we're going to do is we're going to do the velocity. So when we do the velocity, real simple, we just do the first derivative. So hopefully you got that down by now. What's that derivative in your head? -2t plus 4, right? Okay, that's just kind of basic derivative stuff we've learned. So that would be your velocity function, which is a line that's sloping downward. Okay, so we got that. Now on part B, what we're going to do is we're going to find I think we wanted to find the velocity function. We wanted to graph that also. Okay, so let's just do like a graph on the same graph here is what I want you to do. So let's graph this. So you'd have a y-intercept of 4, like that. You'd have a slope of -2, so it would be just going down 2, right 1, down 2, right 1, and so forth like that. So I think I got that okay. So that would be the velocity. Let's label the parabola as s of t, and then the velocity is the line like that. Okay, so we got that. Okay, and then in the second part, what we want to do is we've got the graph. Now we want to do the acceleration. I want to go ahead and just do the acceleration on this too. So when you do the acceleration, that's just the second derivative. So what's the derivative of the velocity? -2, right? Okay, so that means you have constant acceleration. Okay, that's what's happening on that. And that's what happens if you throw a projectile on the Earth, is the acceleration's constant. Okay, it used to be thought back in the ancient world that if you were like on top of a tower and dropped a bowling ball, I don't know if they had bowling balls back there, but the heavier something was, the faster it traveled. That's a lie. We know for sure that that doesn't happen now. So the idea is no matter how massive something is, it accelerates at the same rate. So if you took a bowling ball and a marble, they would hit the ground at the same time. Now if it was a feather, what would happen? Well, the feather would take longer, but that's air resistance. That has nothing to do with gravity, right? Okay, so that is something that we know for a fact. Okay, so let's see. We want to do, this says, in part B it says, when is the object stationary? When does it move to the right? When does it move to the left? Okay, so let's write down a couple things on this. So stationary, we're going to write that down. And when it moves to the left, and when it moves to the right like that, we'll talk about that a little bit. Okay, well, okay, let me stand up on it. I get tired of sitting down all the time. So, all right, this is the curve right here. When is the velocity comes to a stop periodically? Yeah, right, wherever that height is, right? Okay, so that's where you are stationary, which I assume is 2. We'll figure that out specifically. And then when you're going to the right, that means you have positive velocity. Okay, so what's happening on here? Your positive velocity is going to be here. until you get there. So you're going to be moving from the right from there to there. Then you're going to be moving to the left whenever that velocity goes negative. So all it's doing is it's changing directions on that. Okay? So the idea on this would be like this. You would be stationary wherever the velocity is equal to 0. Okay, so you could take the velocity, which we got when we did the first derivative. You can solve that equation. That's pretty simple. I think somebody said 2. I think you can tell visually that that's 2 from my graph. So if I divide by -2, I'm going to get t is equal to 2. So we're stationary at 2 seconds like that. And it's just for an instant of time, right? Okay? Yeah, it just kind of does that. Then it starts accelerating again like that. Okay? So what's going to happen on this then is you're going to the left whenever the velocity is negative. Okay? So that velocity is going to be negative from 2 on forever. Okay, so it's just, I'm just going to write on here, it's negative for t greater than 2, because that's when you have negative acceleration. Okay, and then right is going to be when the velocity is positive. So positive is going to be from where to where? From 0 to 2, so that would just be on the interval 0 to 2. So we'll just say 0 less than t less than 2 like that. Okay, and I'm going to say less than 2 because at 2 it's stationary, so I'm not going to put an equal to bar on that. So I'm just going to go from 0 to 2 like that. Okay, and then 0 we're going to assume that's the initial starting point like that. Okay, so that's what that is basically saying when you're looking at the graph and the direction. Okay, does that make sense? Okay, all right. Okay, and let's see, 2 other things we want to do. Part C, determine the velocity of the object at t equals 1. Okay, so first of all, let's write down the velocity was -2t plus 4. The acceleration was -2. That came from doing our derivatives. So what we're going to do is we're going to find basically v of 1. That's what the problem says, is find the velocity at t equals 1. And then we're also going to find a of 1, like that. These are functions. Very simple arithmetic. So the velocity is -2t plus 4. So if you work out the math on that, that's going to give you 2, like that. And I don't know if I've got the units on this or not. I don't even know if I put units on this problem. I don't think I did. So on this one, it would just be units. You know, it's usually feet per second, something like that. Okay, what's the acceleration at 1? Yeah, it always is -2, right? I mean, there's nothing to plug into that function, so that's always going to be the same. Okay, the velocity changes because the slope of the tangent line changes, right? Okay, you can tell that by looking at the graph. Okay. Okay, let's see. Last thing is determine the acceleration when the velocity is 0. So we're going to find acceleration when velocity is 0. Okay, do you know the answer to that already? It's -2. It's already the same. It's always the same, see? Now see, the velocity was 0. We figured out when the velocity was 0, and that was at 2, right? Okay, but the thing is that since the acceleration's constant, that's going to mean that the acceleration is always going to be equal to that, equal to -2. When the velocity was 0, we found that, I think, to be 2, because that's where the slope of the tangent line was horizontal like that. So that's the idea. Okay? All right, you guys with me on all this stuff? Okay, this is kind of the classic stuff you learn in Calc 1. It kind of prepares you for physics. So I think a lot of you are going to go on and maybe take Calc-based physics here in another semester. Most people do that when they're in Calc 2. And these are some of the basic things that you learn. And you go a lot more in depth in that class than you're doing here, though. Okay, so let's do a couple of more things with this. I want to do one more problem that's got some graphing on it. And then we're going to kind of wrap this up, and then we're going to finish up with a couple of economics applications that I like to look at in this class too. So this is a graph let's go through some things on this, and this kind of helps you interpret the information. Now, S of t, remember, that's a position function. So this is a representation of the position of the object at some time t. Okay, that would be the initial position, and it's going away from that, from wherever that position is. Okay, so what we're going to do on this one is it tells you several things. It says the patrol car leaves at 9 a.m. It's heading north with position function. Okay, and let's see. First thing I'm going to do is going to determine the average velocity of the car during the first 45 minutes of the trip. Okay, so basically right here, that's when t is equal to 0. All right, and then the first 45 minutes of the trip, we would have to kind of look at where that decimal is on here. So like that's 1 hour right there. Okay, so where's 45 minutes? That would be at what number? 0.75, right? 75%, right? So that would be right there. So what we need to do is we need to go right there and go straight up there, and we need to, label what that point is. So that point looks like it is 0.75, comma 30. Okay, so that gives a position right there. And then we got to get this point here, which I think visually you can tell that is 0, 0. Okay, now we've already learned this. We've talked about this a lot. How do you find average velocity? It's a slope of a secant line, right? It's not instantaneous like a tangent line. So we got to do this. So on part A, what you're really doing is you're just doing the slope of that secant line that goes through that. So you apply the slope formula. So that would be 30 minus 0 over 0.75 minus 0. So that's 30 over 0.75. You can take your calculator on that. I got 40 miles per hour. I think this one, I'm trying to think if I gave you units on this or not. I don't think I gave you units, did I? Yeah, I did. It says miles per t hours. That's what it says right there. So it's miles per hour. So this is going to be 40 miles per hour. So like that. Okay? All right. Now the next thing we're going to do is we're going to look at in the second part. It says find the average velocity of the car over this interval. Okay? And then we're going to see if that's a good estimate of the actual velocity at 9:30. Okay? So basically what we're going to do with this one now is we need to just find the points again. So let's look at 0.25. At 0.25, you're here, and it looks like you would be at that point, which looks like 0.25 and 10. So in this one, we have a point 0.25 and 10, like that. Then we need to look at 0.75. We already got that. 0.75, we had the point 0.75 and 30 like that. So we do the same thing. So we're going to do, when we do this average velocity, okay, that's the slope of the secant line. So we just crunch that out. Same thing, slope formula. So that's 30 minus 10 over 0.75 minus 0.25. That's 20 over 0.5. So that would be 40 miles per hour like that. So it's the same idea, okay? Now, the thing that they're saying on this now is that a good estimation for the velocity at 9:30? Now, at 9:30, you would be there. Okay, that's 9 o'clock. The beginning's 9 o'clock, so a half hour later, you'd be at 9:30 like this. Okay, so we're going to see if that's a good estimation. Okay, well, here's what you think about in this then. Okay, what we just did is we found the slope of that secant line right there, right? Okay, what the actual velocity is the actual velocity is the slope of the tangent line at that point. Do they look different or do they look about the same? About the same. They're probably different, but they're really close to each other. That slope is pretty close to that slope of the tangent line, so it would be a good estimate. Does that make sense? Okay. Sometimes it is, sometimes it isn't. So yeah, the idea is those slopes are pretty close to each other at that area. You got the tangent line sloping up like that. So yeah, you would say that's a good estimate. Okay, that's the idea there. Okay, and let's see. Now I'm going to do one more thing with that, and then we'll kind of put together the motion and that kind of thing. So on this next thing, okay, on part C, what I want to do is the same thing with these two times right here. So let's look at 1.75. So 1.75 is here. And let's try to get a good point on that. Let's see what we can do. I'll see what I did on that. I'm going to use like 1.75. What do you guys think? I can't see very good on this thing sometimes. You guys want to settle on 15? Okay, all right. Then the next one is what? 2.25. So that's there. What do you think there? You're going to go with negative 15? Okay, I believe you. Okay, so let's go 2.25 and negative 15 like that. Okay, so we're going to do the same thing. We're just going to do the average velocity. On this, again, it's the slope of the secant line, so you want to go ahead and crunch that out. So that's going to be negative 15 minus 15 over 2.25 minus 1.75. That's negative 30 over 0.5. So that would be negative 60 miles per hour, like that. Okay? Okay, so that would be what that is, and then that says estimate the velocity of the car and determine the direction which the patrol car is moving. So if you were going to estimate the velocity at 11 a.m., well, you would go 2 hours later. So that starts at 9. 2 hours later would be 11 a.m. Okay, so see what we just did is we just found the slope of that secant line. Does the slope of the tangent line look any different to you? No. Okay, so to me, a good estimate, you would probably estimate the actual velocity at 11 a.m. is the same. Okay, that would be about negative 60 miles per hour like that. Okay, I don't see much difference in that, so that would be the idea. And the idea that we've learned is the closer the points get together, the closer you get to what that exact value of the instantaneous velocity is anyway. Okay, so let's see. Let's look at a couple of things on this part D. This is just kind of knowledge stuff that you want to know between 9 and 12. Let me erase some of these notes I've made to myself so I can kind of get this all, so I can look at this a little bit better. Okay, so here's basically what we're doing. Here's 9 a.m. again, and then 3 hours later would be 12 p.m. like that. Okay, so we're going to describe the motion like this. Well, first of all, it looks like, and I'm just going to estimate on here, it looks like right around in here, and let's keep it simple here, so it looks like what's happening on this is on this interval from, on the interval, I'll just use open intervals from 0 to, let's just use 1. Okay, let's just go that way. I mean, it's some sort of decimal. Let's just do that. So from 0 to 1, what kind of velocity do you have? Positive or negative?
Positive.
Positive. So that means that we'll just say from 9 to 10, you're moving to the right. And I think this one in the problem they said that they said it's a north-south freeway. So what we're going to do is we're going to use north as the positive direction, is what they say. So we have that. Okay, then it looks like when you get here, and I'm just going to say that looks like about 2.75. So that would actually be to me from about 1 to about 2.75, which would mean from 10 a.m. To about, that would be what? Now we started at 9, right? So that would be, what would that be? That would be 11:45, okay? So 11:45 a.m., then we're going south, like that, okay? And then finally what we're doing, it looks like from 11:45 to noon, then what happens? We turn around and we go north like that, okay? So the idea is positive velocity, you're going north, okay? Negative velocities, you're going back to the south, and then back to the north like that, okay? You change direction wherever the tangent line is horizontal, okay? Is that logical? Okay? Okay, let's do something with this next problem here. So I did a graph on this one, and I'm not going to do anything with the graphing calculator on this so much. I just wanted to have this there to review, just kind of to explain this. So that's the graph of the position function. If you want to sketch yourself a rough graph, you can. This was going from 0 to 4. Then I had this going from -5 to 5. You don't need to do that in the graphing calculator necessarily, though. So that's what your position function looks like on that interval. Okay, then we're going to graph the velocity function. So really what I did is when I find the velocity, what am I doing with this function? I'm taking its derivative, right? So we want to take the derivative of this function to get the velocity. See, this is a cubic function. So when you do the derivative, it goes down to quadratic. Okay, so this is going to be -18t to the second plus 72t minus 54 like that. That's what I put in my graphing calculator, and I got a quadratic like that. Now we've kind of looked at projectiles, but you could also model the motion of some object with lots of other functions too, like that. So this says, when is the object stationary, when's it moving to the right, when's it moving to the left. So let's make sure we kind of have that down. We're just going to do this visually too. So visually it looks like when t is equal to 1, you got a place where you're going to change directions. When t is equal to 3, it looks like you're going to change directions on that also. So what I want to do is I want to show you the mathematics behind that. I mean, you can go by looks, but it's not generally a good idea. Here's what you would do to find that 3 and 1 on there with calculus. So what you would do is you know the derivative is 0 there, right? Because it's a horizontal line. So what you would do is you would just solve this equation. And let's go ahead and solve this equation. So the solution of that equation should give you 1 and 3, okay? Now let's see, this one I'm pretty sure everything divides by -18. So I'm going to go through and divide everything by -18. Okay, like that. So that's going to give me 0 equals t to the second. That's minus 4t plus 3, like that. And I divide by the negative because it makes factoring easier. I like that t squared term to be positive. That's just the way I do that. So now if you factor that, you would have t minus 3, t minus 1, okay? Now does that make sense? Okay, you get 1 and 3 as the solution of that equation. That's t equals 1, then that's t equals 3 like that. So that's how you would do that then. And then if you're looking at this, we would just say this. We would say we're stationary. Where are you stationary in this problem? There's 2 places. Where is that? 1 and 3 right there. Okay, that's where you change directions. Okay, that's where the velocity would be 0. That's what we just did right there, as we figured out where the velocity is 0. So you'd be stationary at t equals 1 and t equals 3 seconds. Okay, like that. Okay, now what we do, just like the last problem, let's think about moving to the right, moving to the left. Okay, what's going on here? Are you moving to the right or the left? What's the derivative? Is the derivative negative or positive? It's negative. If you have a negative derivative there, that means you're going to be moving to the left. Okay? How about here? Positive. Okay? You have a positive derivative, so that means you're going to be moving to the right. Okay? You're changing directions at that minimum. Okay? Then from here, you go back to negative derivatives. So then from there on, you would have, and this is going all the way to 4, you would be going back to the left like that. So what you would say on this then, you can write this in intervals. So you'd be doing the left, you would be going, and let's use open intervals. That would be from 0 to 1, and then again from 3 to 4. And then we'd be moving to the right from 1 to 3 like that. Okay, so that's the analysis. That's just the concepts of how this applies to physics. Okay, has everybody got that okay? Okay. Okay, let's do this one last example with this, and Then I'm going to go ahead and do a break before we do I'm just going to do one basic business application because that's kind of a good thing to do. So on the next page, let's see, this kind of want to continue and finish up what I wanted to do on this problem. These are some of the questions sometimes students don't do well on because they don't think through this correctly. So we're going to do the derivative, we're going to do the velocity and acceleration at t equals 1, okay? So the velocity is the first derivative, so that's going to be negative 18t to the second plus 72t minus 54. Okay, this time the acceleration is going to be, you do the derivative again, you do a second derivative, so that's going to be negative 36t plus 72 like that, okay? Then what we do is we're going to evaluate this at t equals 1 second or whatever the time is. So we're going to work out negative 18 times 1 to the second plus 72 times 1 and then minus 54 on that. And we'll go ahead and get that one crunched out then. Okay, so I think that one turned out to be 0. Well, that's what we found on the previous page. Remember when we set the velocity equal to 0? One of the answers was 1 second. Okay, you just do that on your calculator. Then a of 1 is negative 36 times 1 plus 72. So that looks like the acceleration is going to be 36, like that then. Okay, so very simple. If you're doing the velocity and acceleration, you're doing derivatives. The one thing I want to show you on this too, I want to scroll back. I'll come right back though. So I want to go back and show you this previous page, the graph one more time that we were doing. So basically, if you look at the answer we got at t equals 1 is we had positive acceleration at that point in time like that. So we figured out that's where the velocity is 0. But at 1 right there, we had some sort of a positive acceleration, okay? Okay, next thing we have is we're going to determine the acceleration when the velocity is 0, okay? We already figured out where the velocity was 0. Where was that? Look at your graph. What did we see?
1 and 3.
1 and 3, exactly, okay? So we already got that. So we know when t is equal to 1 and t is equal to 3, that's when the velocity is 0. We already determined that. So what we're going to do is find the acceleration. So we just plug into the acceleration function, which is right there. Plug it in. Now, it's not going to be constant on this problem like it was in a previous problem. So we just do negative 36 times 1 plus 72. That works out to be 36. And then a of 3, we're going to do negative 36 times 3 plus 72 on that, okay, and I think that turns out to be negative 36 like that, okay. I'm just doing that on the calculator, okay. Okay, let's look at this idea on this last thing here, then we'll take a break. This says, on what intervals is the speed increasing? Now what that means is it really means where is the velocity positive. Okay, that's or the acceleration. When's the acceleration going to be positive like that? So what we want to kind of look at on this one is you're going to try to find where that speed is increasing. You can look at this graphically because all it's really doing, if you look at the graph on here, if you look at your tangent lines right here, the slopes are going to be getting bigger at a certain point in time, and then they're going to be getting smaller at a certain point in time like that. So if you look at your velocity right here, the velocity will kind of tell you that. Okay, the velocity, if you look at this function, okay, the question is where's the speed increasing? Okay, right here you have, right there, isn't that the slope of this? The slope of the line on the velocity gives you the acceleration. So what's happening from there to there? If you look at that, that's a big slope, right? Smaller slope, 0 slope. So what's happening there? Is the velocity speeding up or is it slowing down? Careful, okay. Right there, okay. Slope of the tangent line is big, right? Slope of tangent line 0. So it is slowing down. Okay, right? Then what's happening? Okay, then it starts speeding up because the slope increases, like that. So that's kind of the idea with that. Okay? Okay, so you can do that kind of like this then. So what we're doing on this is, when is this increasing? That's going to be from 2 on out, like that. Okay, so it's going to be decreasing, then it starts picking up speed like that again, like that. Okay, so the answer we would have on that, just graphically, would just be from 2 to infinity, like that, or 2 to wherever I guess the graph stopped at 4, so we'd just say like from 2 to 4 like that. Okay, that's where the velocity is positive. Okay, all right.
I think A of t is the second derivative.
So what I was showing you on this, basically, it's where that second derivative is changed right here. The second derivative, the way this would go is like this. The acceleration would be positive here, like that, and then the acceleration here would be negative from there on out, like that. Okay, so that's kind of the idea. If you look at your initial problem here, once you're going from 2 on out, that slope is changing in a certain way. So let's see, that said, when's the speed increasing? So you can look at the acceleration on this. So basically, when is the acceleration going to be? When's it speeding up? So what do we have on that? Right? So you got positive acceleration there. You got negative acceleration there. Positive acceleration is where it's speeding up. Negative acceleration is where it's speeding down. Okay, so the idea would be speeding up from here to here, slowing down from there to there. Okay, like that. Okay. All right, let's go ahead and take a break here for, let's do 10 minutes. Let's go back about 5 till. Let me show you kind of what this problem is saying. So it's actually very simple. I have the wrong interval on there. So it's saying, when is the speed increasing? There's several ways to look at this. I mean, it's simple. The idea is, okay, this is your position function right here. So what's happening is you have a negative derivative, right? Then you have a 0 derivative, then you have a positive derivative. From there to there, that function is speeding up, right? Okay, because the slope's changing from negative to 0 to positive. And then right there, what we're going to learn a little bit later in the semester, we get to chapter 4, that's a special point. It's called a point of inflection. And that's where the rate starts changing. What happens from here is it starts slowing down. And how come? Because what's happening to that tangent line? It's steep, 0, then negative. You see what I mean? That's one way to look at it. The other way to look at it is look at the velocity. Okay, where's the velocity positive? From 0 to 2. Okay, so it's speeding up. Where's the velocity negative? Like that. Okay, you see what I mean? Okay, so actually the answer where it's speeding up is going to be from 0 to 2. It's slowing down from 2 to 4. Does that make sense? I wrote down velocity is positive. I don't know why I did that. That's where acceleration is positive. Okay, that's where something's going to be speeding up. Okay, so that's kind of the idea. Does that make sense? I got myself confused on that one. Okay, so so on this one should be 0 to 2 is when you're speeding up. Okay, that just means acceleration is positive. Okay, and then 2 to 4 just means it's slowing down. And again, that just means acceleration is negative. Sorry about that. Okay. All right. So the next thing I want to do is I want to look a little bit at one economics application. Okay, like if you study economics, finance majors, I do a lot of calculus. There's a lot of that involved in it. So we just kind of sprinkle in one basic idea in this class, and that's the idea of what it means for something to have a marginal cost, marginal profit and that kind of thing like that. So first of all, there's a lot of definitions. We're just going to do a couple of basic examples on this. So the cost function's given the cost to produce the first X items. Average cost, we usually represent average cost with that bar. Okay, it's kind of like what you do in statistics. If you've taken statistics, if you see X bar, that stands for the average or the arithmetic mean. So that's talking about an average cost of producing items. And then the calculus comes in with the marginal cost that we use as C prime of X. That means we're doing a rate of change of that cost. And that would be the cost to produce one additional item after producing. Now that is a way to approximate that. What a marginal cost is a rate of change on how something's changing over time as you produce more and more objects. But I'll show you what that means is you can use this to approximate. So that's the one key thing that I want to show you. Okay, typically in a cost function, a lot of times cost functions take on this kind of a structure to it. What you usually have is you have a fixed cost, and then you have a variable cost. Okay, like this. And so what this means is, like, if your business was as simple as running a lemonade stand, for example, well, what's your fixed cost? Okay, buying stuff, cups, ice, whatever. What's your variable cost? Well, okay, well, if you had an employee that was doing that for you, you pay that employee. And that employee makes more and more money as you sell more and more stuff, right? So there's kind of that idea. So generally in this one, what we have is we would say the 500 is the fixed cost. And then we'd say the 0.1x, we would say that's the variable cost, like that. So that's generally what you have in a cost function then, okay? Now, what I've got on this, I went ahead and just did a picture of this. This is a cost function. It's linear. As you're producing more and more items, the cost is going up, which should be logical, okay? The more you produce, the more you sell, the more costly it is to you, okay? But that rate could be different depending on how you're running things then. Okay, this piece right here, we call that the average cost. That's just a formula for average cost. So we write that as C bar of X, like that. So anytime you take the cost and divide it by the number of items you're producing, that's called the average cost. That's what averaging is. It's taking all the cost of running your business and dividing it by how many things you're producing or selling, and that gives you an idea of an average, okay? Now I'm going to explain this. This diagram is not on your handout, but I want to use this to kind of explain what this marginal cost, being able to approximate the cost of one more item by this example. And just pay attention to this. The idea would be, if this was just some number, like say that you produced 200 units. So if you were doing 200 units, okay, that cost would be whatever that function value is. So in other words, that would be C of 200. Like that. Well, if I was interested in the cost of one more item at 201 units, well, okay, well, one way to do that would be to just go through and evaluate the function and get the cost of 201. But the other idea is this tangent line right here that you see me drawing on that tangent line would be what we call the marginal cost. Okay, and that's what a marginal cost is it's a derivative, so it's a rate of change. Now here's what I want you to see on this, and see if this makes sense to you. Okay? Are these two function values relatively close to each other? Yeah, they're very close to each other. Now the further out you go, the further apart those values get. But what we do in economics a lot of times is, if we want to estimate the cost of producing one more item, then we can just do the marginal cost and it'll be almost the same. Does that make sense? See, that's the actual cost of 200, that function value. The marginal is just a tad bit bigger. So that's what that diagram's trying to show, is those things are small. Now, it depends on, of course, how the function would be, if it's very steep or flat. But in general, in that small area, if you want to just estimate the cost of the next item, you do take the derivative and then evaluate it at that point. Does that make any sense?
So you want to do it for And you want to do it for 250 units, right?
No, it's just generally for the next one, because once you get further and further out there, it's likely that they changed if they're too far apart. But if you're in pretty close, it's just a quick way to estimate that. So that diagram is intended to kind of to help you with that concept there. Okay, so let's go to the next page, and we'll do a couple of things on this to get this wrapped up. Okay, so this one is a average cost function. So what I gave you on this handout is this is the average cost function. Okay, so you usually represent that as C bar of X. Okay, so what I did is I took the problem that I had on the previous page. So if you kind of look back at what I had on the previous page, I had 500 plus 0.1x, and I'm going to write that down. So I have 500 plus 0.1x. You want to write this down because I didn't really show this. So that's the cost function I gave you on the previous thing. And see, that's a fixed linear function. Again, we said that's a fixed cost, that's a variable cost like that. Okay, well, when you find the average cost, all you do is you just divide by x. And I'm just going to divide each term by x. Then you'll see pretty clearly, I think, how I got that function. Okay, well, that gives 500 over x. The x's cross out here, so you get plus 0.1 like that. So that's what I did to do that. So if I give you a cost function, finding an average cost function is very simple. You just divide by x. Okay, so the idea is the average cost is going to decrease, and you're going to look at your graph of the function I gave you. You can tell that the average cost is declining, isn't it? The y values are getting smaller as the number of items gets bigger. Okay, does that make sense? I'm just talking about how the function goes. As you're producing more and more items, the average cost tends to go down, right? Okay, so that's because of the way that function graphs out. It's got an asymptote, and it's approaching the x-axis, basically what it's doing, okay? So the average cost gives the cost of items already produced, and that's going to give you really a slope of a secant line. So this right here, this average cost is really giving you like just a slope of a secant line, like we've learned about. Okay, and then if we're doing the cost of producing additional items, that's when we get into the derivative. That's when we get into the marginal thing. So whenever you take the limit of that difference quotient on the cost function, then you end up getting the marginal. So when I'm taking that limit, that's giving me the marginal cost, so that's given a derivative. Okay, so a marginal cost is a rate of change of something, so it's represented by a derivative then. Okay, so this quantity right here is what's going to give you the marginal cost like that. Okay, all right. And then the other thing, and I've already talked about this, I guess, here, so the average is like a slope of a secant line, and then the marginal describes the slope of the tangent line at that particular point. Okay, so it's kind of got the same principle behind it that we've learned with derivatives. So I'm going to do one example. I don't generally do too much with this in this class. If a student takes business calculus, I mean, you do this quite a bit more extensively. These are the type of applications that you look at. Okay, so let's see. Let's go on to the next page. I'm just going to crunch out this last example here. And this is the kind of thing I expect you to know how to do. So first of all, what I'm giving you on this one is I'm really given this. This is a cost function. Now, the cost function doesn't have to be linear. It can be anything, okay? That's a quadratic. That's a cost function. And then this thing right here is going to be a price function. So I've given you a cost, then I've given you a price. So a lot of times prices vary. You know, in the world of economics, prices fluctuate up and down depending on how many things you sell and produce, okay? So what we're going to do, first of all, is we're going to find a profit function. We're going to work with a profit on this particular problem. So first of all, what happens is you have to know a couple of basic formulas, okay? And this is logical. The profit When a business figures out their profit, what do? They look at two things. Revenue. What is revenue? That's how much money you are taking in, right? And then what else? Cost, okay? You got to subtract those two, okay? If your business didn't have any cost to it, then your revenue would go in your pocket, right? But you got to subtract off the cost. So the profit is just the revenue minus the cost, okay, like that. That's the way I think of it, okay? That's important. So then the other thing is we got the revenue. Okay, so the revenue is this, okay? Let's go back to the lemonade stand. How do you compute your revenue in a simple business? It's just how many things you sell times the price of that item, right? A cup of lemonade's 20 cents, you sell 200 of those, you multiply and you get the revenue, right? So what we do on that is we just say the price, of the item times the number sold. Number of items sold like that. So that's what basic revenue is, okay? So if we formalize this a little bit, then it's going to go like this. When we make a function, R of X, that's going to represent my revenue. Now what that is that's just the number of items we sell. And that's what X is. That's the number of items. Okay? And then P is going to be a price, and generally that's represented by a function. So we're going to say that's a price function like that. Okay? So that's kind of the idea of the mathematics behind this. Now in this problem, they've given you the formula for profit. I prefer that you figure it out. Okay? I think that's a better way to learn that. So then what you'd have for the profit is, when you do a profit function, and that'll be capital P, I'm using a small p for the price function, then that's going to be the revenue function minus the cost function. Okay, it's revenue minus cost. So the revenue is XP, okay, and then the cost is just going to be whatever that cost function is. Okay, so what they've done is, see, they've given you that formula right there. Okay, I don't ever think of the formula that way. I just think of, I need to know the revenue and the cost to find the profit. Okay, I don't even think you need to look at that formula. Okay, all right, you guys with me so far?
Yeah.
Okay, this is basic simple business kind of stuff. Okay, so what we're going to do is we're going to find the profit function. So when we find the profit function, the first thing you got to do is you need to find the revenue. Okay, what I've given you is I've given you a price function. So what you do is you do X times P. Okay, revenue is X times P. So we do X times that price function, which is going to be that. So that's what the revenue is. If you're given a price function, you have to crunch out what the revenue is. Sometimes you're given a revenue function. So that revenue is now going to be, if I multiply that out, distributed property, that's 100x minus 0.1 x to the third like that. Okay, so that is my revenue. Okay, all right. Now what I need to do is we need to find we're supposed to find the profit function on this. So the profit function is the revenue, which we already got, minus the cost, which I think you were given in this problem. So you were given a cost function. Typically you are. Okay. So what I'm going to have with this then is I'm going to crunch this out. It's just basic algebra. We're going to take the revenue function, which is 100x minus 0.1x to the third minus, and then the cost function is this quadratic that you were given, negative 0.02x squared plus 50x plus 100 like that. Okay? So what we're going to do is we're going to kind of clean that up. We're going to do the like terms. And then the rest of the problem is going to be working with that revenue function. Okay? So let's go ahead and just put the like terms together. Okay? You can do that in your head, or you can take a couple of steps. I'm just going to change the signs and then combine the like terms. And I'll write that like in a descending order like that then. Okay, so let's see what I have here. It looks like I've got, let's see, I think I got everything right there. Okay, so let's see, I've got negative 0.1x to the third. Okay, then I've got plus 0.02x to the second. Then these like terms go together for the x's. That looks like that's plus 50x. And then minus 100. Okay, so that is the function that's representing the profit. That's some sort of a cubic function, and that'll represent the profit. The business's profit is fluctuating depending on how many items they sell. X is how many items you sell in that problem. Okay, so we got that. Okay, is everybody solid so far? Okay, all right. Profits, revenue minus cost. Typically, cost is given, revenue you have to compute, but you're typically going to give given a price function. Okay. All right. Now, what average profit is? So in this one, we're going to find the average profit and the marginal profit. Okay. So the average profit, we usually write that as P bar X. That's the average profit. Okay. What we said we do on that is we divide by X. So you're going to take that profit function that we have, and you're going to divide that by X. That's the definition of what an average profit is, okay? So what I'm going to do is I'm going to do this. This is something you can do in your head, but just to show you what I'm doing is I'm going to take the profit function I have over here, up, and stop that. That's going to be plus 0.02x squared over x. Oops. Okay, then I'm going to have plus 50 over x, and then minus 100 over x like that. And I'm just going to clean that up. Like I say, you can do that in your head if you want to, because all you're doing is taking the polynomial and dividing each term by x. Okay, so let's see. If we do that, what do we have? Negative 0.1, and then what? X to the second, right? The exponent's going to go down 1. And then 0.02 times x. The x's cross out there to give plus 50. And then I'm just going to leave that as 100 over x. You could write that as a negative 1 power, but we'll do that when we do the derivative. So that would be what the average profit is then. Okay? Okay? Everybody okay? Okay? So the next thing we're going to do is we're going to do the marginal profit. So the marginal profit means take the derivative of the profit. Now this is not asking for the marginal average profit. So we're going to take the profit function we have over here, and then we're just going to do its first derivative. Okay. So if we do this, we're going to have negative 0.3 x to the second. Again, just doing a power rule. 2 times 0.02 is 0.04x. Then the derivative of 50x is going to be plus 50 like that. Okay, so what I've got is I've got these two things. I've got the average, and then I've got the marginal like that. Marginal means find a first derivative. Okay? Okay, all right. Is there any questions about that? Okay, derivative is pretty easy. Okay, so now what we're going to do is we're going to find the average profit and the marginal profit at x equals A. Now I think A they gave you 500. So in this problem you were given, that's the area, that's the place that we're interested in. So we're basically working with 500 units. So we want to do these two things. So what we're going to do is we're just going to work out P prime of 500. They want you to do the average profit is P bar of 500. We're going to work that out. And then the marginal profit, we're going to do this. Okay, so all that means is we're just going to plug it in. We'll do this in the calculator. Some of these things I'll have to work out on my calculator. Okay, so if I do the average profit at 500 units, I'm going to plug into this function I got highlighted in yellow. So that's going to be 0.1 times 500 squared plus 0.02 plus 2x plus 50, and I got to plug in the x of 500. And then if you want to go ahead and take your calculator, you can go ahead and do that on this one. Then we'll do the next one as well. I'm just going to do this in one step on my calculator. Okay, like that. Okay, so I think I got everything plugged in. I just replaced x with 500. And then when we do the marginal, we're going to plug into here. So that's going to be negative 0.3 times 500 squared. Then I'll have 0.04 times 500. Okay, and then plus 50, and then I'm just going to crunch those two things out on a calculator. Okay. Then we're going to do one last thing with this. I'm going to do the concept of estimating, using the marginal to estimate the 501st term like that. Okay, so let me put this in. So I got negative 0.1 times 500 to the second plus 0.02 times 500, and then plus 50, and then minus 100. You can just put 1/5 if you want to. I'm just reducing that fraction in my head. Okay, so let's see what that is. That's given a negative number. Okay, that just means if you have a negative profit, what does that mean? It means you're losing money. Okay, you're in bad times, right? Okay, so that means that's about negative 24,000. Well, you're doing pretty bad. Your business is not doing so hot now. Okay, so we got that. All right. Then the next one, let's see, negative 0.3 times 500 to the second, and then plus 0.04 times 500, and then what, plus 50. Okay, so let's see if we get the right thing on this. Okay, now that, when you're doing a marginal, that's given a rate of change. So that's negative 74,930. That's a rate of change. We would expect that to mean that if you graphed out this function, this profit function, that it would be sloping downward. Okay, when you're selling 500 objects, that part of the graph is sloping downward because you have a negative sloping tangent line. That's real steep. That's a really big number right there. Okay. Okay, so that's the idea. Okay, so basically what I want to do is show you one more thing. These are just the typical things you do. We don't do much with this. Is if we find the average profit, I think we already found the average profit for selling those items, and that turned out to be negative 24,940.2. Just means you're losing money, you're in the red. So if you want to approximate the profit, now what we're going to do is we're going to approximate the profit on the 501st item. Well, then what you got to do is you got to do this, okay? The thing that we got to do on this is we would have to differentiate our average profit, and then we would have to evaluate that at 501. What we're going to do is we're going to do this P bar prime of X like that. So we're going to do that. Okay, so that's our P bar like this, and then we're going to evaluate that at 501 like this. Okay. Okay, so here's the idea. Let's go ahead, and when we do this, we need to differentiate the function I've got in yellow. So we got on this one, we're going to have negative 0.2x plus 0.02x. Okay, then the 50, the derivative of 50 is 0. And then when you do like the negative 100 over x, you're doing the derivative of negative 100x to the negative 1. So when you do that, that's going to be plus 100x to the negative 2 like that. Okay, so that's what the P bar prime of x is. So that's negative 0.2x. I'm going to clean this up and write this like this. Now see, what we're doing is we're not finding the profit on, we're not finding the exact profit on the 501st item. I'm showing you that if you do the marginal of that, okay, that's our profit function right there. That's the average profit function there. So if we do that derivative, that's now the marginal average profit. Then I can plug in the 501 as an estimation. Yes?
Shouldn't that be just 0.02, not 0.02?
Yes, thank you, thank you. Okay, I get a little sloppy sometimes when I'm doing that. Okay, yeah, that's 0.02 like that. Okay, so what we do now is we do this. We're going to do this marginal average profit at 501. And what that'll do is that will be close to the value of the exact profit value at 501. Okay, so what we're going to do is do 0.2 times 501 plus 0.02. I think I'm missing my negative. Did I miss my negative? Yeah, because I know that should get a negative answer on this. So I've got this like that, so I'll take my calculator and do that. So let's see what we get here. So let's see, plus 0.02 and then plus 100. Then that divide by 501 squared, that thing's going to go pretty close to 0. And let's see kind of what we get there. Okay. So it would be about like that. Now what's happening on this is that approximates the profit of the 500, of the average profit of the 501st item.
So this is a good thing because it's actually, if he did 502, he might actually start making some money.
Well, it's good. What's happened is the slope is changing pretty fast on this one.
It's actually really terrible business. The more business he does, the less money
He produced one more and lost 100 extra bucks.
Yes.
Oh, okay.
Yes. Yes. Yeah, that's what's happening. So, yeah, what that's doing is he's losing that amount of money. Okay, like that. Okay.
So for every one he does, he's
Right. Right. Okay, that's the idea. Okay. So that's how you can use that marginal to approximate that value like that. Okay. Okay. Does that make some sense? Okay. Okay. So I'm gonna close